know the deep understanding. Yeah, that's why. So the attention mechanism calculation is just like this. Oh, it looks very I can say that it looks very difficult, but I would I would to be easy to talk this. Okay. Wait. Let me to open a plant. Okay. This is attention mechanisms. So attention mechanisms have an algorithms. Algorithms is attention. This algorithms it will have algorithms is equal to what? Anybody know? It's softmax and q k transpose and the kd and times the v. Is that like it? It sounds difficult, but don't worry. I will introduce why this works. Okay. So before we talk about these algorithms, first we should know what Makara is no. Is no. Hey, wait. Hey. Hey. I tried to pair in here. Okay, just use this pane. It's okay. Okay. So for softmax, this is I can say this is properties output. And now we should to know the first is about the Q K V is about the query key and value. So what is query? What is query? See here. So sometimes, for example, it's Tom. I might say Tom and Jerry. And my name is what's it? Tom choose Jerry. Tom choose Jerry. Okay, this is a street talk, right? Tom choose Jerry. Tom choose Jerry. If I want to translate it, translate. If I want to translate these three words, Tom choose Jerry, what will happen? What will happen? What will happen? The Tom will be another language, right? Because in the different language it's different. So I will introduce that like the Tom. For the Chinese or maybe for the different, it will be different. But okay, such as we talk about like in Chinese, like Tom, Chase, Jerry. It's difficult for the Chinese. It's like this is a Jerry, this is a Chase, this is a Tom. Okay, just like that, Tom, Chase, Jerry. But for some different models, not in the attention mechanisms, it's like what? Like yesterday we talked about the RN, right? The RNN. Anybody remember the RNN? Okay, we opened yesterday, and you see. Let's see the RNN and first. Okay, this is the RNN. In yesterday, we don't talk too much about RNN, right? And maybe you cannot have a deeper understanding of that. But today, we will now introduce the RNN. So what is RNN? RNN is user neural. It's a news every neural. This neural is to input some things that we call it token maybe here. So in the RNN, if I use Tom, Chase, Jerry, and when it comes to next models, we wanted output. They'll be like here, like this one. It's Tom. You don't need to know what this means. It's just a term, just a term. Tom, Chase, Jerry, the Chase. This is Chase, right? Tom, Chase, Jerry. Okay. And we should know this is x1, this is x2, this is x3, right? x1, x2, x3. This is understanding, right? x1 is a token, x2 is a token, x3 is token. Yeah. Should be understanding? It's easy to understand, right? x1, x2, x3. This is 3 tokens. And before we input into the this neurons, we will do y is equal to the w1 x1 plus b. This is the Rn in the Rn. And we call this y. It's actually not y. Actually, it should be h1. This is h1. This is h1. h1 is this one. h1. Okay. See here. See this Rn. Okay. See. It's different with the CNN, right? In the CNN, we input imaging, but for the CNN, it's not very equal to the text generation. So we need to use a different tab. It's like this RN. It's a recurrent neural network. So the H1, remember, the H1 will include the information about Tom, right? Right? Yes or no? Yes or no? The H1 expression, when we use a function to make the Tom be a vector, this is a vector, okay, to be a vector, this H1 will include the right. Will include the right. Yes. Oh, yes. Okay, it's yes, okay. And see here, this is the H2. We call this H1, H2 is we call it a hidden state. Okay, hidden state. Why is hidden? Because this hidden state we can't see by our eyes. It's directly seen, right? Because this H1, H2 is just a vector. We don't know the meanings. Just the machine, just the model will know, right? He will know, oh, H1 is for the information of the Tom. The H2 is the information about the Chase. So in here, see in here, the recurrent neural networks, see here, the second one will include the informations for the H1. In here is ST, right? ST minus 1. This is ST minus 1. This is the ST. So the next one, H2 will equal to what? Based on this one, it equal to what? It will be equal to the, for this, it's the what? Tell me. The H2 will equal to what? See here. This is the ST. This is the HT. H2 is equal to what? Anybody know? Type it. Okay. 1 minute. 1 minute. The H2 will equal to what? H1 times ST minus 1. ST minus 1. In here, we don't have a ST1. ST minus 1, right? In here, we don't have it. Okay. So H1 W2 plus W2. Oh, very good. Very good. This is the right answer, but you use a different, maybe not W2, maybe W3. Okay. Yeah, W2 is also good. So for the recurrent, why we call this a recurrent? Recurrent because the next hidden state will remember the next hidden state will remember the previous one's informations previous the H2. Okay, previous H2. So the H2 will equal to the W H1 plus W X x2, right? The x2, right? x2 and plus a b and use a function, maybe it's f. And this function we use is a tanh. Tanh, okay. Tanh is also an activation function, just an activation function. We use this tanh. Tanh is like this one. Are those hidden Markov model? No. It's not the Markov models. It's not the Markov models. Okay. The hidden state right. Yeah. So we use the tanh. Remember? I remember the sigmoid is like this one, right? And the sigmoid. Okay. The sigmoid is like this. The sigmoid is this one. Sigmoid. And now we will have a ReLU and a tanh. And we use the tanh as the activation function. So the tanh will look like this. Okay, the tanh will look like this. Oh, wait. It's a little. Wait. Just use my pen. The tanh will look like this one. Okay, so see, the sigmoid is from 0 to 1, right? It's bigger than 0 and less than, smaller than 1, right? And the tanh is greater than -1 and smaller than 1. So it is also just a activation function. We use it to output, add some nonlinear factor, right? This is the activation function, and we get the H2. But why we need this? Why we need this? Think. Why we need add the H1 to the H2? Why we do this step? Why we need to do this? Do we need the contact and the recurrence? Yeah, we don't. To keep track of the privacy. Yeah, that's right. So like in the CNN, we don't do this. We don't do this because the higher feature map will include the previous information, right? But in the recurrent, we also want to do the same thing. We want to check the information and we want to remember the information. It's relevant information, right? So the H2 add the WHO2 H1 and the X2, right? So the H2 will include what? The H2 that will include the information about the X1 and X2, right? Even in the H3 is same, right? Is string. And when we get the H3, the H4 will have the ability to translate the output is the Tom is cheese. This is Jerry. This is Tom, cheese, Jerry in Chinese. Okay, in Chinese terms. Okay, if you are interested, you can search it. Maybe you choose. Yeah, maybe you can use the application. You translate the Tom, cheese, Jerry, but in Chinese, yeah, it is this one. Okay, but this architecture, it has a weakness. It has a weakness. What weakness? For this architecture, it will have a weakness. What weakness? Why it have weakness? You can say that H1 remember H2 remember H1, H3 remember H2. It's very good. What information? What weakness? Why it has weakness? It's very good. So much computation, too much memory overloaded. Oh, cache information or past information. Yeah. Yeah, that's right. Yeah, that's right. You are very smart, I think. Yeah, that's right. It's overload. 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 Yeah, it's overload. And the RNN can only remember the short sequences. And there is one thing that is you should to remember is this neural. This neural, every one and every neural just can store a little information. Just store a little information because one it comes to a very long context. When one comes to a very long context, what will happen? What will happen? When it comes to a long context, there is someone said, "Oh, vanish green is very good. It's a very high level. It's a very high level happen." Yes, it is. So think when we have a long context, long sequence, long sequence input, what will happen? Oh wait, what will happen? What will happen if I use a long context sequence? What will happen? Big value. So much information. The last one don't use some info. Yeah, that's the reason. Yeah, and we call that is uh it will forget, right? It will forget a long-term memory, right? It don't have the long-term memory, and also will cause vanishing gradient. What is the vanishing gradient? It means that if the neural is too much, if the neural is too much, and when we make the neural one by one, for the last one, went to the BP algorithms to the first one. The gradient one is all the gradient is smaller than the one. The gradient will be so smaller, and the weight of the agent will not change anymore. Okay, so it will have two problems. It's a forget the long-term memory. It will not have the long-term memory abilities, and it also has some vanishing gradient. Okay, so we should to use attention mechanisms. So the attention mechanism is the first proposed in the sequence to sequence these models. And let's see the attention mechanism to do what? See here. Let's do this again. Actually, we also use Tom Chase Jerry. Okay, we also use Tom Chase Jerry this example. Tom. Okay. So in the attention mechanism, we have a query, key, and the value. This is a three very important keyword for this mechanism. Okay, so the Tom will be the query. The Tom also will be the key, and the Tom also will be the value. What that means? It means that the Tom, it's the X, right? The X1. The X1 will times the WQ be the query. And the X1 Tom will times the WK will be the key. And also the X1 Tom will times WV will be the value. Why we do this? Why we do this? Okay, we will talk. We will talk this things. Why we do this? So let's keep going. But the Tom is the token, right? It's a word. It can talk not to calculate with a matrix. So before we start to use the attention mechanism, we have a very important step. We call it embedding. We call it embedding, right? Embedding. There is one very important thing that we call the embedding. And then nowadays, not only the embedding, we don't use the one hot, right? Before we have import in one hot. Also, we have the word to vector, right? Word to vector. It's all the embedding models that we will use. But just to remember, we will have a embedding. So in the embedding, the word will be transferred to a matrix. The word Tom will be a matrix. Will be a matrix. But actually it's just a vector. Okay, it's just a vector. Is that a vector? Okay, just a vector, or maybe a matrix. Okay. And let's keep going. So the attention mechanism calculation producer is to use the query. Use a query. What is query? What is query? For the Tom is query. Tom is query. Let's have a review about the RNN. If we want to translate the time trajectory, what will we do? How to translate? We will use the what? We will use the hidden state 3, right? H1, H2, and H3. We will use the hidden state H3 to output the answer, right? We use H3. But in the attention mechanism, it's different. The query will have attention with the every key, the key 1, key 2, and the key 3. What that means, the key 1 is Tom's matrix, and the key 2 it's a Chase matrix, and the key 3 it's the Jerry. Okay, what's the difference between this attention mechanism with it's the RN? What's the difference? Q Tom. What the difference is? In here, we will do what? In here, we will do what? In here, we will do a what? Reference a key. Oh. Attributes is still the context correlation. Yeah. There's a relation of the relevance comparison. So in here, it's a different. See, the Q and do a dot with the K. The query Q1 will do the dot with K1, and the Q1 will do a dot with K2, and the Q1 will do a dot with the K3. What that means? Why we need to do this? Okay, now we need to come back to the mathematics. So if two vector is if there is two vector, there's 1, 0, 0, and the second one is the 0, 0, 0, right? These two vector we call it what? Is non-correlated, right? Non-correlated. None. So white dot will be what? The A dot B will be what? Will equal to what? Tell me the answer. To be 0, right? To be 0. Yes, it will be to 0. But if the vector A and the vector B, this two will have the correlated 1, 1, 1, and 2, 2, 2, right? There is correlated, right? It's double, right? So Y8 dot, what's the answer? Dot. Still dot. Still dot. What will happen? The answer is what? Not 2, 2, 2. We use dot. We use dot. We don't use the matrix times. Okay. It will be to the 6, right? It will be to the 6. So we use the Q1 and the K1 to do the dot is to do what? Is to get what? We let the Q1 and the K1 to do a dot is to find the what? A number is not a number. It's want to find what? Yeah, I see the answer. Yeah, we want to find the similarity. We want to find the similarity because we see that if this two vector is different, is non-correlated, it will be 0 or maybe a very small number, be 0, 0, 0.001. But one it correlated. One it has correlates or correlated. The similarity will be very small, right? And it will be maybe a high number. It will be a high number, not a vector. The times this dot is not. It will be have a what? It will be a very high number. It's a big number. It will be maybe 47 or maybe this one. Okay, it will be very higher. Okay, we not talk about in metric. We talk about in vector. Okay, it will be very high numbers, right? Understand? Any question? Any question? Not that. Any question? If some of you are not understand, you can ask. Why we need to do this? Why we need the query Q to times to dot the Tom, to dot the Chase, to dot the Jerry, the key 1, key 2, key 3 is to find the similarity. Is to find the number and to find the importance. Okay, to find the importance. To find these two terms, these two words, the similarity, and to find that what's the importance of the Tom for the Tom? What's the importance of the Chase for the to the Tom, and what's the importance of the Jerry to the Tom? Understanding? Understand? Yes. Okay. So yeah, I still don't understand what represent Jerry key and value. Okay. Okay, I believe that someone maybe not understand why we need to do some operations to the query, to the key, and to the value. Okay, this is abstract. This is abstract because we want to use a different. We want to use a different represent. We want to different represent to show the query key and the value. Okay, okay. We cannot just use the Tom to dot for the Jerry, right? Because this is embedded. It's just when we embed it, it's just a vector, right? When we embed it, it's just a vector. We cannot make this two vector just to do a times or to do a dot because these two embeddings will not have any many meanings. So we need to have a W. This W is the weight of the query. It's a weight of the query. It's a weight. It means for the query, I want to focus how many queries I want to focus. Okay, because the query will be many different. Because maybe this time is Tom, Chase, Jerry. So the different will be like I love studying and I want to watch movies and daddy loves moms, like this different. So the W, this W is this WQ, the W key and the WV is to find the patterns. Okay, to find the patterns during and the inherent the relationship and the inherent meanings of this sentence. Okay, understand? Actually, and if we don't use the WQ, if we don't use the WQ, it will be have. We can just do the x1 to dot the x2, the x Tom, the q Tom to dot x Tom is still we can do this one. We can do, but will not very good. And for the experiment, it will choose bad. Okay, it will choose bad. It's a bad idea. Okay, it's experience. Okay, it's an experience, and that's the scientist said that to use the WQ will remember more information of the input. Okay. Yeah, there is three types of the embedding. Just but yeah, that's right. There's three types of the embedding. Yeah, just maybe the for the query we want to show what. Okay, for the key we want to show what. For the value we want to show what. Okay. Yeah, we want to maybe in the query we want to focus on the information is maybe for the query is to show this one, but for the key we want to show the different information, right? Because you want to search and you want to find the importance and find the relationship. So the key will be different, and for the value, just I want to focus how many, how much, and how importance of this word. Okay, just the three types, and just to make the model. This is for the model to understanding. So now we have got the this is the soccer, right? Score. This is the score. This is score. But the score is different because the score is what? It's maybe very high, maybe it's 100, maybe one, maybe 22, like this, right? So in here, this score will do a very important algorithm. So we call it softmax. Softmax. So what is softmax? Softmax is to make the all the element, like all the numbers to be a normalization, to be normalized, to be normalized. Normalization is what? Normalization is to make all the numbers, the sum of all numbers to be one, to be one, to be one, to be. It's ugly, right? To be one. Okay, to be one. And this algorithm is look like this one. Is sigma e I yes, sum is equal to 1 and I equal to 1 and to the I, and for the E I, right? EI. Okay, like this one. This is should be J, not Y, maybe. J. Yeah. Like there is 4, 3, 4. So when we use a softmax, it will be 4 plus 3 plus 4 and 4, right? For the first score, it will be equal to how many? 4 under 11, right? 4 under 11. And then for the second one, it will be 3 under 11. For the last one, it will be 4 under 11. Understanding? It's very directly thinking, right? Just to get the probabilities, okay, to sum equal to 1. Because if I use 100, this one is 1, this one is 22, it's not balanced. It's not balanced. Okay? And it's unfair, right? It's unfair. 100 this importance is very big, but just the one is not very big. And we want to use a very fair. We want to use a fair to show everyone's important. Okay, and to make every element the sum will equal to 1. Okay, understanding? Someone is not understanding type 1. Okay, if you're not understanding type 1, if you're understanding, say yes. Okay. For the softmax, yes, to make the embeddings comparable. Yeah, right. Yes. So here, what we do is just to make every score, right? To make every score is to normalize with yes, right. It's like normalize with yes, just this. We make every score has the same weight during these mechanisms. Okay, so when we use a softmax, it will equal to what? Just maybe 3, 3, 4. Okay, it will be 0, 3, 0, 3, and 0, 4. Yes, 0, 3, 0, 3, 0, 3, 0 0.3, 0 0.3, and 0 0.4. Okay, and it also can be seen as a what? can be seen as importance, right? It can be seen as importance. Idiot, right? It can be seen as the importance. Okay, the Tom for the Tom is 0.3. The Chase to the Tom is the 0.3, and the Jerry to the Tom is 0.4. Maybe Tom and Jerry have a very high information, right, and a high similarity. Okay, but this information and this important score, this is after training. It will be get after training. Okay, before the training, maybe it's 0.9, 0.005, 0.005. It will be happen. It will be happen. But it's normal, it's common. It can be accepted because we're not training our data very good, right? So it will be have a different value when we not finished our model training. Okay, understand? This score is after the training we will get it. During the training, the score will not equal to the real and to the finish that we get. Okay. Okay. Delete it. So there is a softmax. Actually, softmax also can be seen as the activation function, right? 334. We use 334. Okay, we use the 334. 003 00 30.4. Okay, now we get to the importance about the Q, Q and the key 1, Q and the key 2, and Q and the key 3. Now we're going to use the value. So the value is what? The value is about the word itself. Okay, the value is about the word itself. So in here, we use the attention mechanism to do the 0, 3, 2 times the key. Sorry, it should be value. I'm wrong. 2 times the value, the value, there should be, it should be 0, 3 times the value chase. And the last one should be 0.4 and value Jerry. Okay, then it will be a matrix. And this matrix will include all the information, right? It'll be a matrix. A matrix. Okay. Okay, so now the attention mechanism is over. But why we needed to do this? Why we needed to do this? Why in the last we also needed to do this one? Because in here, think. If I want to find a book in the library, and this book is about mathematics, the first thing that we will to find the most similar with this book, right? We will find in the library which gadget and which line is the most similar with the math, the high math, with the high math is the most similar, right? I want to find this one. So in here, it's the same thing that I want to find which is the most similar to get the score, right? And the score maybe it's maybe the Jerry is most higher. Okay, and now I know that every book. I know that every book similar with the book I want to find it, and I want to do what? I want to make every book times itself. It means that maybe this a novel will include the math, but it's not very similar to the books I want to find, so I will use 0.5. And this Chinese is no mathematics, so maybe 0.3 or maybe 0.1, or maybe this is the real about the derivation I wanted, maybe 0.3 or maybe 0.9 will be most probably is right. Okay. So in here, what we want to do is to find the relationship, right? Okay, see, come back. So in the attention marketing calculator, we do the same thing. It's just a three step. The first step, what we do is to calculate the similarity between the query and the key to obtain the weight. The weight, it means what? It means the importance, right? To get the importance. To get the importance, right? To get the importance, use the softmax. Like Tom and Jerry, you are very Tom Chase Jerry in Tom Chase Jerry, the Tom and the Tom, they are same word, right? So it will have a high weight, and the Tom and Tom will not have a very high. Similar with the Chase, maybe Tom will have a high similar with the Jerry, just like this. Okay, so we get the weight, and the next we normalize the weight obtained weight that can be directly used is to use the softmax, right? And last, perform the weight sum of the weight and the value, just to get the value, and now we can get the attention value. And in here, in the first, we talk about attention or equal to what? Or equal to the curve and the key across, and there is under dk. Okay, here. What is under dk? What is this value? Why we need this? Why we need this one? 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 Remember, in the attention mechanism algorithms, we use q dot the k transpose and divide under dk, the root dk. Why we needed this? Anybody knows? Anybody know why we need to divide root dk? Stabilization. Actually, half right, half right. If you can explain more and clearly, can you explain it clearly? Stabilization is right. It's right. To make them comparative normalize, to normalize it. Okay, so in here is to make prevent attention stalkers. Actually, the root decay is to make the training more stable. More stable. Okay, we should come back to the math and to influence why it's more stable. Okay, see. So in here, in the first, our data set and our input will have a very important value. We call it average. Average is a mean, right? And also we have a variance. And we call that STD, right? An STD. So we want to do what? We want to make the QK will have a it's deployed in the average equal to 0 and to the STD, the variance equal to the 1. And this is just the assumption, okay? That's just the assumption. That's the assumption. It's just assumption. And what we want to do is to calculate the variance of all the Q and K. How to calculate is to get the VAR with the QI and the KI, right? So every QK when it comes to the sum, the variance will be DK. Okay, will be DK. Okay, again. If the Q and the K, the every element is deployed and along the value, the average will be 0 and the variance it will be equal to 1. And so give the every QK, give every Q case a point, a score. Give every QK a score, it will have a very high variance, and the variance will be decay. To understanding? To understanding? Again, okay? Again. Like the Q for the Q1 to the Qn, the average is equal to 0. The variance is equal to 1. For the variance of for the average of the K1 to the Kn, the average is equal to 0, and the variance will be 1. But the Q1 times the Q1 times what? The Q1 times the K1, right? And get a sigma from I to N. So this sigma and their variance will be what? Will be decay. What is decay? What is decay? Decay, it means the dimension. Dimension is the dimension of the K, okay, of the K. Decay, the dimension of the K. Dimension. Okay, what is dimension? Dimension is means how what's the size of the decay? Maybe the decay is 1 times 1024. So the decay will be 1024. Okay, this is the hidden dimension. Okay, the dimension. What is the dimension means? Dimension means we use how many and how big the dimension that we want to express this decay express this key. Okay. For example, maybe there is a matrix 1 times 1024. This is a vector, right? This is a vector. And I'll use this vector to express a word or to express a sentence. So I can use this many numbers to express I love studying. Right? I can use this too many to express I love studying. But if I just have the 1 times and 12, maybe just the 12 numbers. If I want to explain the I love studying, it will be easier or harder? It will be easier or harder? Or difficult? Easier? Are you sure? If I use I use this way, I use just the 12 dimension to express I love studying, it will be easier or difficult? Think. You should notice that this vector is not only express the I love study, it need to express all the sentence, all the word. Okay, I need to use 1024. This vector, I need to use this dimension to express all the information and all the sentence. I need to use this dimension. Okay, so it will be more good, right? And the 12th dimension will be difficult, right? Because there's too much information. There's too many words. I cannot only to use just the 12, this dimension is number to express all the sentence, right? So understand what is a dimension, right? Understand what is dimension, understanding? The dimension means that I want to use how big or what's the size of this metric to express this information. The dimension, when it becomes bigger, the information will be more conclude more detailed information, right? Understanding? Any other have question? You can ask now. You can ask now about this one, okay? So the information, the dimension, and the information is to do this one, okay? Now we know the dimension, right? We know the dimension. It means we can express more. We can express a lot of things, right? So come back to here. So come back to here. If our query and the key have a big variance. They have a big variance. Okay, they have a big variance. When the Q times the dot the K, the value will be very big. It will be very big. Okay, it will be very big. It will be very big because the variances become very big, right? When the variance become big, the Q and the K, their dot will be a very great number, will be a great number, will be a great number. Understand? Understand? This is for the mathematics, okay? This is for the mathematics because when the Q and the K, when it have a high variance, they are very different. They are very different. So when it dot, the output will be great. It will be great. And why it be the great? For example, I think for example, give example, it will be better. Like if the Q1 times K1, the Q2 times K2, if it will be 1000, it's just be 1. The Q3, K3 will be 2. Why to do the softmax? What will happen? The first one will be a proximity to the 1, right? And this second one will be equal to what? Will be a proximity to what? It will be 0, and then the third also will be 0. But this is not the things we expect to, because the distribution will be like what? It will be very shape, like this. Okay. Every other things will be 0. Just the one value be 1. So other tokens, it means that we will not focus and we will not care. But we don't want to do this. So we divide a decay. So it will when divide a decay, then it will be 10. It will be maybe 0, 1, 0, 2. But it's close, right? It's close. It's close. So it should be maybe 0, 8, 6. This should be 0. Maybe 0.08. But it's more close, right? It will be more close, these two, right? Want to be more close is that our information will be have some influence to output. Okay. And the Y is not decay, it's root decay. It's because our standard variance should be equal to 1. So we use root decay, not decay. It's also a trick. It's a normalization. Normalization is also a normalization. Okay. So this all is the mathematics trick. Okay. It's all mathematics trick. Okay. So what we're doing here is to understanding the attention values importance. Okay, it's a little difficult, right? It's a little difficult. Yeah, it's true, but I believe that you can understanding even after classes. You can also to search it. Okay. Okay, want to have a break? Want to have a coffee time? If you're not, I will keep going. Okay. Okay, time limit. We don't have copy down. Okay, we keep going. So now we will know the attention in machine learning translation what will be happen. So here, in the translations, we used a very important is the sequence to sequence model. That the x1, x2, x3 the input will be a vector, and the encoder is to to embedding the x1 to the another express of the x1 to the x4. It's a vector, and the decoder is to translate the vector say context. Vector say is means the vector context to translate the vector context to the output y1 to the y3. Okay, like in China, Chinese is hello and ni hao. Okay, understanding ni hao. Yes. So this script is general purpose to encoder and decode the word. They often used in the narrow visioning and text abstraction. So the text-to-text model, originally is a script-to-script model. And the encoder converts the input variable length script to a context vector, which was the mechanism which encoder to the input vector and encoder vector to be the output. Okay, like two step. Okay, is understanding? It's or no? It's just to make the our input text to be another express of the for in the models. Yeah, and repeat it. Yes, again. So the encode is to it's based on you can make the vector's dimension be bigger. It can be smaller. It's up to you. Okay, it's up to you. Maybe the input maybe here. Can you here? See it? Okay, so maybe here, maybe in the first, the input dimension is 1, 0, 2, 4. Okay, maybe this is the input dimension. But when we get to the vector, maybe it's maybe be bigger, maybe 4, 0, 6, 96, right? Maybe like this one. Maybe 0, 40, 96. It will be bigger. Not only be reduced. Okay, it will be bigger. Okay. And it means that the text embedding is use this dimension to express all the input, but the encoder will extract the information during this text and to be a higher dimension to express all the information. It's a vector. But this vector, this context, is that we can understanding? Can you understand this vector? Can we? Can you understand or can we understand? Do you think you can understand the vector's meaning? No, because why? Because this vector, it was be embedded and be encoded. It's an encode, okay? It's an encode. It'll be oh ugly. It's ugly. Okay. Wait. It'll be encode. Encode, right? Encode. It be encode to another format, and this format can be only understood by the models, right? Can only understand by the models, not by the what, not by our human, right? It's a format just to can be understanding for the models. So like the encode, like we can be a secret, and our models can understand it. But the decoder is to decode, right? To decode this vector to the output to be the text that we our human can understanding. Okay. Okay. It's close to machine language or not necessary. Um, mm, uh, Mm, for the first, for the RNN, for the RNN, for the RN, for the RNN actually is not necessary. But when it comes to higher understanding for the models, the encoder-decoder architecture, it will be have a high accuracy. Okay, it's not whether about necessary. It means it's about that if we use the encoder-decoder mechanism, it will have a high performance. Understand? It shows a high performance of this method, so we use it. Okay, it's not that necessary or not necessary. Is that we think that is better, so we use it. Okay, and so here we can repeat. Okay, understanding a lot. Okay, so in here, the working principle of the encoder and the decoder is like this. So see here, I have a LSTM model. So remember, the LSTM models is like RNN. It's same. It's same. One LSTM. It means one neural, like the RNN. Okay, this is RNN. This is RNN's architecture, right? The LSTM just the architecture of the RNN, like this one. And we output a vector. This is a vector. This is a vector. And this vector is contain all the informations in the this 我很好 this I'm good this one okay I'm fine it's good. This thematic vector C is contain all the information about the input, right? Input, about the input. And when we use the decoder in use this function to output I am fine. Okay. Did you output this one? Yes, and no vanishing gradient. Yes, because we use it's not no vanishing. It can be prevent, not no. Okay, not no vanishing. It can be prevent, but it will still happen. Okay, we can make it be more harder to to happen. Okay, okay. Understanding everyone? Okay. So we use this encoder to decoder to make it to be like this one, and we can use this we use to do this one, and the why we use the LSTM. Why we use LSTM? Because the LSTM is this is a transform. This is another transform of the RNN because the basics RNN's architecture will have a very high problems about the vanishing gradient. Also will have a explosion gradient. Yeah, the two problems will be having. So we use LSTM. The LSTM will be better. Okay, because the LSTM will be more stable. Will be more stable. But this encoder decoder will also have the problem, right? It also have a problem because the semantic vector it cannot right? It cannot do what? It cannot contain all the information, right? Because if I have a paragraph and if I have a passage and this passage was maybe 1 million or maybe 10 million is too much, maybe 10,000, okay. Why I have a 10,000 text when I want to translate this package with these passages, it will be very hard, right? It will be very hard. And maybe it's impossible, right? Because this semantic vector C, maybe just 1696 this dimension to express the information, right? If I have a 10,000 paragraph, it will be do. Can it do? Maybe it can do, but it will be bad, right? It will be bad. It cannot translate good. Also cannot output a very good paragraph, right? It cannot good. So the encoder decoder, this encoder decoder architecture, it's it's a framework. It's a framework. It's a framework. It's not specified models. So in the transformer, we will use this encoder decoder framework, but during the RNN or during the LSTM, we can say this also will be happen to the not have the long-term dependency, and the context vector cannot represent the information of the entire input screen. Okay, understanding? And for the attention mechanisms, we also use the sequence to sequence, but now most of the models just use the decoder, not the encoder decoder architecture. Okay, let's see why we do this. Okay, so the attention mechanisms like the in the encode decoder we will do things, and we just to have a review. Okay, so for the first, the encoder, see here, the encoder to the decoder, this architecture just use the semantic encoding, this context, right? They don't to focus, right? They don't focus the Y1 output. They don't focus the Y1. Does the Y1 have the information with the X1 or have the X2 or maybe the X3, right? This is the weakness, right? So for the information about how to concentrate and how to focus on the information that we wanted, that we use the attention mechanisms on the encoder decoder. Okay, have a review. See, so in here, the Y1, see, the Y, what is C1? What is C1? Now I believe you know. What is C1? What is C1? C1 is a context, right? C1 is a context, but this context is about the output Y1 with X1, the output with X2, the output with X3, the output with X4. This 4X will have a attention with the output. Now we can get it. Now let's see how to do this one. So we still have a understanding of this one. See, if I want to translate, also use to translate this example. Okay, so I want to know. Well, I want to translate how are you, is talking, right? And this is also symbol. And the BOS. What is BOS? BOS. Anybody know what is the BOS? BOS. It means it's anybody know the BOS is what? What is BOS? For the output, what is the BOS? Okay. The BOS is the beginning of the sentence. Okay. It means this is a symbol means our, yeah, the beginning, yeah. The BOS is means our model needed to be, it needed to work, and our model should start to translate. Okay. This is mean the BOS. And the BOS, this BOS will have attention, right? Will have attention with every what? With every what? With every what? With every, tell me, the BOS, this token will have a attention, have a dot with what? With every what? Every input, right? With every token, with the how, with the R, with the U, and with this symbol, right? With every input, right? So in here, we can get a what? We can get a attention score, right? Attention score. See? We can get attention scores and about the BOS with H, the BOS with R, and the BOS with U. And this attention score is look like what? It will be maybe 96, 11, 23, and 55. Okay, 55. Okay. And after the softmax, it will be a probability distribution, right? And the sum will be equal to what? Be equal to 1, right? Okay. And now we can use this softmax this to focus on the encoded hidden state. And this is means the value. It means the value. It means how important of this word. Okay, how important of this word. And in the last, we can do is to do attention output. Okay, it's attention output. That's the thing that we talked before, right? And now we can get to the next one. Is how are you? And this is the chatbot. It's a chatbot. It's not a translation. It's a chatbot. So if I say how are you, you will say I. Also, I use I to do this one. The next one will be maybe I and also be fine. Okay. Again, understanding? We say again, okay. See, the BOS, this symbol, this is just a symbol, and this symbol is defined by human. This symbol is defined by human, okay? This symbol is defined by human. And this BOS is also a token. The BOS is also a token. If I input any sentence, if I input any text, we will set the BOS before the output, okay, before the output, and the BOS will to get the attention with every word and get attention output, and this attention output will based on this one to get the output decoder hidden state, and this one will be I and I to get the IM fine, right? Maybe you are curious about why we can get this RM file, how to get it. Now we can see that we have attention. This attention output, this attention output is a vector. Is a vector, and this vector is like this one. This vector is like 1 times VH. What is VH? V it means the vocab. Okay, the V is means the vocabulary, and the H means the vocabulary is hidden state, and the vocabulary will we have a vocabulary, and this vocabulary will include all the words we will use. Okay, all the words we use. Maybe this vocabulary maybe is maybe 8, 6, 3, 5, 2. Okay. Maybe in English there's just this word we will have. Also, not only English word, maybe the symbol, maybe the minus plus this symbol is also will be in the vocabulary, right? And during this 1 times the 8, 6, 5, 3, 2, in this vocab we can use a softmax. Okay, we can use a softmax, and every position for this vector. This vector is 1 column and 1 column and no, not 1 column, 1 row. Sorry, 1 row and 8, 6, 5, 3, 2 columns. And after the softmax, every IDX, for every position will be a probabilities, right? And we will get the most probabilities ones and to search in the vocabulary and get the most probabilities of the next one. Okay, understand? Maybe maybe there it will be a little fast. Okay, should I say again? Where are you? Again, please. Okay, again. So, what do we want to do? Yeah, what do we want to do to output is to output the most probabilities, right? The most we think that is probability, right? We want to output is the most probabilities, right? We want the most probability because the most probabilities means that I think this next token, if I said how are you, the I it should be the most follow the logics, right? Most from our human to think that to say I'm fine is the best answer, right? I'm fine is the best answer. Also mean I'm good or I'm okay. This will also will be the best answer, right? I will not say not say like fuck these things, right? Right? Maybe just a maybe, but for the logics, I will say I'm fine. Okay. right? So in here, what you want to do is to get the attention output. Is to get the attention output. And the attention output is concat attention output with decoder hidden state. What that means? It means that the attention output, it will be a vector. It will be a vector. Why do this one? It will be a vector. And the vector, it will be, the size is 1 times the VH. And the VH is the vocab size, right? If I want to output the word, I need to know which word is the most probabilities, right? Which one is the highest probability that I can get. Understand? This can be understanding, right? This can be understanding? Yes. Anybody? Anyone know? Yes. Because I want to find the word in the vocabulary. How to find? I want to know every word's vocabularies, which one. So I have a vector, and this vector is 1 times the VH, right? And the VH is the size of the vocabulary. Maybe our vocabulary have 10,000 words, right? Maybe our vocabulary will have 10,000 words. This can be understand, right? Have 10,000 words in our vocabulary. In our vocabulary, maybe I have 10,000 words. So this vector, it should be, the size is 1 times 10,000. 1 times 10,000. Okay, 1 row and 10,000 columns. Understanding? Understanding? Yes or no? Yes, right. Okay, yes. So if it's every vector in here, every vector in here, every number in here, it shows a what? An importance, right? Shows a value. Maybe 1, 11, 24, and 41, and 21, and blah 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 until to the last one, right? It shows the attention circle, right? Attention output. It shows the attention output, right? For the every word, right? For the every word's position. Understanding? Understanding? And it is after training, okay? In the first, it's not true. In the first, it's not true that it will get the best answer. It will be the wrong and it will be false. But when we train it, it will be more close to the true answer. Okay, and the index of the specified position, it will be have a higher and have a more higher score of this position. Okay, understand? Every position is mean. Is this used for the imaging output as well? For the imaging, it's different. Okay, it's different. It's not same. For imaging, it's not same. We don't use it for the imaging output. For the imaging output, we will use we call it VAE, like this one. Okay, we use the decoder is VAE or other things, not only the vocabulary. Okay, in here we just talk about the NLP. Okay, we just talk the NLP right now. Okay, so for here, every position is shows a probability or shows the importance. So when we use a softmax, right? When we choose a softmax to this last the hidden state, we will get probabilities of each one, right? So the first one may be 0, 0, 1, second one 0, 1, 2, 0, 0, 8, and 0, a tall one. Okay, I in there I can get everyone's probabilities, right? Every position's probabilities, and I have 10,000, right? 10,000. Have 10,000 this vector to shoot all the probabilities, right? Yes or no? Yes, can understanding? So now I get the now in this vector, I get the most probabilities, right? I get the most probabilities. I get the most probabilities of the maybe in the index 4. Maybe in the index 4, right? Maybe in the index 4 is the most probabilities, right? Maybe index 4. Maybe in the index 4. Index 4, IDX 4. Maybe the index 4 is the most probabilities, right? So I can search it. I can search it in the vocab because in the vocab every word will have its own index. Maybe in the 4, maybe it's I. Maybe in the 9, it's maybe in the index 9 is it's love. Maybe in the index 11 it's um bulk like this is like this. Okay, so in here, this vector it shows the probabilities of the every words, right? So I can search which one is the most probabilities in this vector, and I can get the index, and I can use this index to search in the vocab, and I can get the true word. Understand? Okay. If you have any question, you can ask. Okay. If you have any question, you can ask. Any question right now? Ask it. You can ask. Okay. And maybe maybe someone still have a little confused. You can ask her anytime. Okay, anytime. You can type on the screen, and I will see it, and I will answer it. Okay, I'm going. Okay, I'm keep going. So right now I can use these things to calculate, but now the transformer it will be used different. The breadth of the transformer is in 2017. You all know, right? And the transformer is different. The transformer is not only use of the attention. We call in the transformer we use is self attention. It's self attention. It's different with attention, but it's a little similar. A little similar. So in the first, we can see that in here we have input and we have input impedance. So the input impedance is to make the word to be matrix, okay, to be the word to be matrix, but the sequence will be the word will be vector, but the sentence will be the matrix. Understand? The word, the term will be a vector, but you know that a sentence a sentence will be many word, right? A sentence will be combined by many word, and it will be a matrix. Okay, understand? I will show you. I will show you. Maybe see here. See here. Maybe there is a matrix, and it's what? Maybe this matrix is 10, 24 times 40, 96. So this 10, 24 is means the word length. Okay, the length. It means the length. Understand? It's a length. It's a length. It means the length. So maybe the first is today. Maybe today is very good. Like these things. Okay, understanding? Every every line, every row is represent one word, and the columns the columns is from 1 to 40. 1496 is means all the hidden state. It means the hidden state. Okay, I use this hidden state to represent this word. Okay, understanding? Understand? Yes or no? If no, I will explain again. Okay. Yes. Okay. So in here, I use input embedding, right? Okay, understanding the input embedding, right? So the input embedding, it also can be is also after training. Remember, the input embedding is still after training. After training, when we training all the models, the input embedding will still be training. So like the x1. Remember in here the x input actually will be equal to the w embedding. We have an embedding matrix. The w embedding will times the x input, the x in the origin input. Okay, the origin input. The origin input. Actually, the input of the index, the input of this one is also just a word, a vector, sorry, a vector. And this vector actually is like 1 and 47, 517, like these things. Okay, blah blah blah. Why is it? Why is this? Because the real token, not the real word, we can't input directly. We must transfer the word to be a digital number. Understand? Understand? The word we cannot input directly. We must transfer it to be a digital number. We call this step, we call this encode, right? It's encode. It's encode. It's encode. So why it be transferred? What it will be? It will be based on the vocab, right? Remember, in the vocab, every word have their specified position. Maybe for the I is index 4. Maybe for the bulk is index 17. Understand? Every word will have their own position. Okay, understand? Okay, I think I should be slowly because there is a little difficult, right? And anybody think this is easy? Anybody? So now the input vector, it will be showing as every single number, right? Like 137, 517, like this one, right? So this is the vector. This vector is maybe 1 times 1000 times 24, like this. Just like this, okay. Just like this. This is a vector. And after this vector, we will have a position encoding. Okay, we will talk later about the position encoding. Now we just skip it. We just need to know the position encoding is to add some information about the position, like the Tom chase Jerry and the Jerry chase Tom. If we don't add some position encoding, it will be same. Okay, again, the Tom chased Jerry and the Jerry chased Tom. If we don't add the position encoding, it will be same, right? Understand? Because the Tom, when we use embedding to transfer it to be a matrix, it's white in the different position. It will be a same vector, right? If I add some position encoding, it will be show the position meaning. Understanding? Understand? The position encoding is why we need this. Yes, okay. Yeah, you're all smart. Okay, so in here, the transformer. Now we come to the first is a transformer block. It's encoder. It's encoder. So the encoder contains the n equal to 6 identical layers, and the layer refers to the unit on the left of the figure. This is encoder. I need to confirm that you can see my pen, right? You can see my pen. Can you see my pen? See my board? Can you see my pen? Yes or no? Okay. Maybe maybe I use my mouse to draw this thing, so maybe it's not very beautiful. Okay, okay. Next, we have a decoder and we have an encoder. So the encoder in here is to encode the things, is to encode the input, and the decoders in here is to output the things. Now let's see more clearly. See, the transformer workflow will have 3 steps. The first step is to get input, is input like I said, and the second is the encoder. Is to transform the input to the encoder is to be a encode, text, and this encode text will be include all the information, right? All the information of the X, and we can use this X to the next one, to the decoder to explain what that means. Okay, and the step 3 is to transform the coding matrix to the decoder, and you can see that the decoder will be more complex. So let's see one by one. So for the transformer, see, now I use machine learning to be as a example. So what we're doing here is to use the word embedding. The machine will be embedding a vector, and the learning will still be transformed embedding. Understand? And also we have an encode position, and we add the position encoding to the machine vector, and we will get a new vector. Okay, we will get a new vector. And in here, we don't plus it. We make it to be concat. How to spell concat? Concat. Okay. Understanding the concat? We use concat. Also can be seen as stack. Stack. We stack this one. We stack, not concat. Actually, stack is more clear. Okay, we stack these two vector because it's a sentence, right? Okay, so the first row is the machine, and the second row is the learning, right? Understanding? In there, it can be understand, right? In here. It's very clear, right? It's very clear. So now we know the machine and we know the learning. What's the vector and how to represent the machine and the learning? Okay. So next we can see that the word embedding. And in the word embedding, we have a different method to know. Like in here we have the word to vector, and we also have the global vector. This is this area is two models. This is two models to do the word in many things. Okay, and now actually when we will use different. In nowadays models we don't use word vector and globe. Okay, because this is outdated. Okay, and we just know the word embedding is also needed to be training. It's all need to be training. How to training this? Like we can see that we have a Sable. The Sable and the Skip grammar is two models is based on the word to vector. This is all based to vector. So in the Sable, in these models, we have a training method to I give you the input. I give the input from the t minus 2 to t plus 2 and t minus 1, t plus 1, and I give you this 5 word. I give you 5 word. And you should predict the middle one. Okay, you should predict the middle one. Use these things to training this method. Okay, use these things to training. And I like basketball. I like basketball. Okay, there is basketball. I like basketball. Anybody like basketball? Anybody? Rather than football. Okay, other than football. Wonderful. Just example. Okay. So the rather it will be delete when we training. So I will give the model but I like so there should be I like basketball in here, and then football. So the model should predict the rudder. Okay, should be predict the rudder, and we can use this method to training the embedding method. Okay, okay, understanding? Okay, we blanked one middle and use this way to training the model. Okay, use this ways to training the model, and we can understand in the embedding method. Okay, any question? Any question? Let me see. No question? No question? Okay. So in here, next we should to know the position encoding, but this will be a little difficult. Okay, but for the transformer, we used is the absolutely position, and in here, to make the every word have their position meanings, we use cosine and sine. We use the cosine and sine to know the index meaning. So how to say that? Just see this one. This is the sine. This is sine. So for the every word, it will have a position, right? For the every word, it will have a position. For the for the twos, the I to I from 0 to the length, contact length, right? We will have 0 to length. Okay, and we will get the position encoding sine sine position divided 1/10,000 and up to I divided dimension model. It's a dimension model. So in this method, we can know that the different position will have a different meanings, right? The different position is represent the position of the word in sentence, and the D is represent a dimension of the PE. The PE is seen as a word meaning. It is seen, okay. Just the position encoding. And in this way, we can add the meanings of the position. And the 2I represent the even dimension, and the 2I plus 1 is represent the odd dimension. I know that you will confuse why we use the sine, why we use sine and why we use cosine. Because like see here, if I draw to the sine and the cosine, if the sine will be look like this one, right? And the cosine will be look like this one. Hey, sorry. Cosine will be look like this one. Sorry, just like this one. It should be like this one, right? Like this one, like this one, like this is the sine and cosine, and this 2I divide the dimension model. This is our t, right? This is our t. Understand? This is our t, and the t it means a cycle. It means a cycle. So this under this one is the cycle of this other information, but the different position of the 2I will different. Okay, maybe from I 0 to I to the biggest is maybe 10 24. The different position, their meaning is different, so it will be not same. They'll be not same. Okay, it will be not same. But actually, in this method, we'll lose some information. We'll be lose some information because, like here, if I give example, I like reading, and I'm very happy. For this, for this, information, this I and this I is same. But actually, this I and this I maybe have some relationship. But in here, use some absolutely position coding method. It will be not reference the relationship. So nowadays, we now actually we don't use the position coding like this way. We will use some not absolutely. We will use how to say that, a very relative position encoding. Yeah, relative position. We not use the 2i, this absolutely index of the position. We will use the word I, the word one of the word, and the word is maybe 4. We will use the 4 minus 1. Use this way to calculate this index positions, the meaning of this position. Okay. Okay, of the position coding is just like this, but and if you, I believe that maybe some of you are not very clear about this because it's a little difficult, but you can search it. Okay, we should keep going, and the biggest things will coming, and the next one is the encoder. Okay, the encoder, and you are and now you know the encoder, right? You have already know the encoding is what, and but in the transformer, the encoder will be different because we used it as self-attention. It's not attention. We used it as a self-attention mechanism. It's not attention. So for the self-attention mechanism, it's used to calculate the dependence between the element of the input screens and each word. It means that what? It means that in the input, it will be calculate the information. It will be calculate the information. Calculate the information itself with everyone, with animal, with didn't, with cross. The animal didn't cross the street, it was too tired. Okay. But in the attention mechanism, remember, in the attention mechanism, we just calculate the attention in which part. Okay, give me some reply, okay? I know you're very maybe it's difficult. But in the attention, we use the in the attention mechanism, we use the attention in which part? We use it in the input or not? I mean, in the attention mechanism, we use this attention mechanism in which part? In which part? Input? No. Okay. In the attention mechanism, we don't, not self-attention. In the attention mechanism, we use it in the output. Remember. Okay, let's come back to see. In the see here. In the attention mechanism, we use it in the output. Okay, in the output. In the output, we just use it about the BOS with how are you, the I with how are you, the I'm with how are you, right? We just use the output about the attention mechanism to know what is the relationship with the prefer with the before in the previous input. Okay, understand? Okay, we just want to know if I want to translate or I want to text generation. I want to know what's the relationship. Understanding? Understand? Yes. Okay. Yes. It means that it's okay. Again, I need to say again. In here, in the attention mechanism, there we just use the attention mechanism to find the output, the relationship with the input, right? Because without the attention mechanism, we use a what, right? We use a what? We use a context vector to translate, right? We use a context vector translate, but we found that a very small context vector cannot translate all the information and cannot contain all the information, right? So we use a what? We use a encoder, decoder, and we use the attention mechanism, right? To find and to capture the key and to capture the important things about the how, maybe how are you with the I, with the M, with find these things, right? Okay. Understand, right? Understand, right? This is attention mechanism. We just use it in the output. We just use it in the output. Okay? We just use it in the output because in the input, we still use the RNN based architecture or maybe LSTM. Okay. What is RNN? Well, RNN is the HT is equal to the WT minus 1 times HT minus 1 plus WTXT plus B, right? We use this one. This is HT. This is HT. HT minus plus 1, HT plus 2. Okay, understand? HT plus 2. Understand? This is HT minus 1. This fourth circle. This fourth circle. Okay, understand? Understand? Okay, understand. Okay, now. So, but in the transformer, in the self-attention, we will not use RNN in this architecture anymore. Okay, we will not use architecture of the RNN anymore. Okay, RNN is a recurrent, right? Recurrent. We use RNN. RNN is based on what? RNN's information is based on the previous neural, right? We use the previous neural to know the information about the whole sentence, right? Right? We use the previous neural to represent all the information, right? Understand? Because it will be one by one to give to the next one, okay? But give to the real one, right? The real one. It will give to a real one all the information based on the previous, okay? And in the self-attention, it's different. We don't use this. See, so in the self-attention, it will be have different. So here, let's have a review. And here, the machine will, and the learning will be have a x1, x2 in mind, right? This we all know. We all know this one. We have already know, right? We have already know. Understand? This is already know, right? We have embedded, right? And this embedding will be to the Q1, Key1, and V1, right? And we use Q, query 1, and the key 1, and the value 1 to do this information and to get the score, right? Should be understanding? This is a dot, okay? This is a dot. We have talked before. Right? In the beginning, we have talked. Now we have just a review. Okay, we have a review and to find maybe somewhere you don't understanding. Okay. Okay, and if we have a dot, we get a score, right? We get a score. We get a score, and this score is a point, and this point may be very large and very great. Let's say here it's 1, 1, 2. This is 96, right? 96. So in here it will be hard to calculate. So we should to use a very important thing is to divide by root dk. Okay, root dk. So the root dk is like I'm saying that we want to make the training more stable. So to divide the root decay, it's because the dot will be bigger. It will be greater. The dot's number, the result will be greater. If the The decay is what? The decay is means the dimension. For directly thinking, I know maybe you are still have a very maybe you're not very understanding about why is decay. What is decay? Okay, just to give an example. Okay, maybe our dimension is just a 4. So the 4, the dot maybe 1 1 1 1 2 2 2 2 is what? How, tell me the dot. The dot is 8, right? The dot is 8, right? 8, right? This is just the dimension is equal to 4, right? But to see this situation, if the dimension will be 1000, this vector will be 1 1 1 1 1 1 1 is equal to 1000, and if just the second will be 2 2 2 2 2 2 2 equal to the last one. Tell me the dot. 2000, right? So you can see if the dimension it will be bigger, right? If the dimension it will be bigger, it means that our score will be very greater. Understand? Now you can understand, right? Now you can understand, right? It means that if our dimension is be bigger, our score it will be also be very big, very greater. And when it be very greater, our number will be hard to calculate, right? And this when it be very big, there will cause a situation I have talked before. Okay, this can be understood. Should I say again? Should I say again about these things? The dimension about the decay? Should I say again? If you're confused, you can say. I can say again. Okay. Should I say again? Say again. Yes. Okay. Say again. Okay. Okay. We still use this example. Okay. If our dimension, remember what is dimension? Dimension means we use how many dimensions to express one sentence or maybe one word, right? We use how many numbers to express this information meaning, right? To express information. Maybe 4 dimension to express I love studying. It's difficult, right? I use this 4 will be difficult, but I use 1000 dimension to express I love study is easy, right? It's easy because 1000 will have more numbers to express the different positions the meaning, right? Understand? This can be understood, right? This is I talked before. Understanding? It means that more information, more dimension can be expressed more clear, more one word, more dimension can express more information, right? Okay, understand, right? Understand. So if we want to store and we want to let the model remember more information, we'd better to use a higher dimension, right? We will use a higher dimension, right? A higher dimension. But see here. If I use 4 dimension here, if I use a 4 dimension to calculate the K, so it will be 1 1 1 1 2 2 2 2. Just an example, okay. This dimension is still both 4, right? So the dot will be 8, right? The dot will be 8. Understand? The dot is means what? The dot means the Q and the K, the concurrency, concurrentness. Okay, the concurrentness. Okay, it also means the relationship. Okay, when it have a higher relationship, it will be a very bigger score, right? When it no non-currentness, it will be a 0, right? Understand? It should be understand, right? Should be understand? Yes, right. Yes. Okay, so in here, I use a 4 dimension to calculate a number. I calculate the score, it will get 8. But we do an assumption. If I have 1000 dimension, If I have 1,000 dimension, 1,000 dimension is the number I set from 1 to 1,000 is still 1111, and the second one is 2222. So you can see that to compare with the dimension is just 4, the dot will become 2,000, right? This can be understood, right? If I use a higher dimension, the score will be higher. Because the number be more, right? The number be more, the score will be greater. Right? Of course, yeah, of course. Because the number be more and more. So the score will be very bigger, be very great, right? Understand? Understand? It's directly thinking that four four numbers dot will be smaller and the 2,000 number will be greater. Okay, so in this way, we can see the score. If I use higher dimension, it will be harder. It will be harder to calculate, and it will be very greater. So we want to divide by the root dk. The dk is the dimension. Remember the reason I said before. If the number be too big and the other one just a 1, just a 2, just a 4, it will be like one hot encoding. What is one hot encoding? It's just a 1 be 1 and the other all be 0. Remember? If this is too higher, we after the softmax it will be 1. All the others will be 0, right? But it's not the things we expected, right? We want to the distribution be more smooth. The distribution be more smooth. Every token, the attention score will have their own point. There should be more smooth, not just one token to occupy all the information. Okay, understand? Understand? Because if 2,000 is too big, it will be like a proximity to 1, and the other one just to be 0. The 0, 1 will no influences to the end. Okay, so this is the why I think this is why we use the root dk. Okay, the root dk is to scalar. To scalar is to scalar is to scalar or scaling scalar, yeah, scalar is to scalar. To scalar the score not be too big is to make the score be more close. Okay, the score be more close. Maybe 2,001 be 100 and 0.5. They're just be more close, right? This one is 2,000 times. This one just maybe 200. It will be more smaller. So it's just a mean to reduce high values and decay depends on the right. Yeah. It's just a mean to reduce the high values and the dimension decay depends on the hidden. Yeah. Yeah, it's like stabilized to avoid so big scores. Yeah, right. Just this thing. That's like they say. Okay. So in this way, we can make the score, make the score, and make the last softmax the probabilities and the importance of the everyone to be more stable. The distribution will be more stable and keep the biggest and the most important is to make the gradient to be stable. The gradient to be stable, okay? If just one is too big, just one is too big, the gradient will so easy to do the back propagation because just one is big, but the other one is smaller. It's hard to training. Okay, because this one is too higher, too bigger. Is to make the training be hard to train because the other one is equal to 0. If equal to 0, the gradient will approximate to 0, right? And it will be harder to training. It will not update anymore. Understand? Understand? Should I say again? Understand. Oh, smart boy. Smart, smart. Okay. So in here we got the importance, right? We got the importance of the x q1 and the key1, q2, q2 and the key2. Now we can do the times. The 0.88 will times the value v1 get the z1, and also same with the v2 can do the z2. And now in the last, the actual matrix operation is like this one. It's the q is a matrix. Okay, q is a matrix, and why we needed to transpose, because the q actually is the thin shape. Actually, the q is the same shape with the k, so we need to transpose the k to make the qk can be and do the matrix operation. Understand? This can be understand, right? This is just just a high math. Okay, just a high math. This can be understand, right? Right. Is it right? We need to transpose the k to make the q, and the k can do the matrix operation. Okay, so the q do the matrix matrix multiply with the k and divide the root dk and get the softmax. Now we can get the score, right? And the score times the value. Now we can get the z, and the z is means what? Z is means the last attention sum up. Okay, attention sum up. Now we can use the Z to do this thing. So now we know the self-attention. But so why we need why it works? Why it works? Why it works? To use the math to describe these things maybe is so abstract, but just to remember, the self-attention just to do what? It's just to do what? Have 1 minute to think about what the real the real things about the self-attention. What's the self-attention do what? It is do what? What exactly the self-attention do? What exactly? To analyze the context of the outer world. This is the one. Yeah, actually, I think I'm right. It's good. It determines the relevance of every other word. Yeah. Understand the context of the sentence. Differentiate the input element and the focus. Yes. Just use one word to conclude to do the conclusion. Just to make the every word be described by the other word, right? Right? Again, just make the word to be described by the other word. Be described. Okay, understand? To be described. The machine learning, the machine is described what is learning. And for the machine, the learning was described what is machine. Okay, understand? Like I love you. That's I love you. So the you will be I described. The you will be described by the love. And the you will have the meaning of the I and I love. So the you will know, oh, it's you love me. Okay? Understand? Like the I like basketball, like this thing. So it's just to describe. Okay, describe. Every word, every one word would be described by all the other word. Yeah, Dana, you're very good. It makes possible to determine the very important word to focus on them by getting the context for the word around it. Yeah, not around, for the all. For the all. All the word will describe other word, include itself, right? This is a self-attention. This is a self-attention. Because that we can know what is the token related. Because the machine, because the learning, because every word will to know the relationship with the other word. This is the self-attention. Is I call it a describe. Maybe you have your own insight. Maybe you have your own opinions, but it's okay. Just to know that every word has been described, has been modification about every other word, right? Understand? Understand? Because one it come from the x1 to the z1, the meaning is changed. The meaning is changed. The z1 will include the other word's meaning, right? So the z1 will know, oh, the machine will have a relationship with the learning, and the learning will also know, oh, I have a relationship with the machine. Okay, that's the self-attention. Okay. So okay, let's have a compute. Okay, just to do like the x1 to do with the WQ is what? Okay, 2 minutes. Okay, give me the answer. The x1 times the WQ, the x2 times the okay, not too. Okay, let's calculate together. Okay, the time is limited. Okay, so this is the 1 times 4, right? This is 4 times, just calculate the 1 is okay. Okay, this is 4 times 3, right? 4 times 3. So first is 1 0. It should be 1, right? Should be 1. The first is be 1. 1 times 1 is 1. 0 times 2 is 0. 1 times 0 is 0. 0 times 2 is 0. So first should be 1, right? And the second is 0, right? Second should be 0, right? Because 1 0 is 0. 0 meant for 0. Okay. Okay. It's so fast. Okay. 1 0 2, right? Okay. The second one is same, right? It's 4 4 0. It's so fast. Okay. This is self-attention. Okay. This is self-attention. Okay. Understand this is self-attention. And remember, this WQ is after training. The WQ, this weight, it will be changed. This weight will be changed based on the back propagation. Understand? The weight will be changed. Okay. And because the weight is have a very huge matrix, the matrix may be maybe 4096 or even 112 to like very huge. The weight matrix will be very huge, so it can know all the information of all the world. Okay, understand? And that's why the large language model will have so many parameters, and the large language model will be so big, so great. Okay, that's the reason. And also it will have the reason because of the transformer, the self-attention will have too many parameters during the transformer block. We didn't just have one transformer block. We will have 6, maybe 100 or 1,000 transformer block to know the relationship during the x1, x2, these things. Okay. So now the next thing is to generate the queries, key queries, and the keyword. So the query vector will do these things, and to do the same things. Okay. The next. Okay. The step 1 is to generate the query key and the value, and the second one is to calculate this one, right? The query vectors will calculate with the do the dot with this one. It's 2, right? It's 2. Okay. The dot query and the key is 2. The dot query and the key is 4. The dot query and the vector is 4. And the 2 will do a softmax. Next step is do a softmax, right? So after softmax, this one it will be what? Tell me. After softmax, it will be what? Remember softmax. Softmax is sigma E I and EI. Okay, I equal to 0. This one will be what? The first one should be, remember, all is 2, 4, 4. The first one should be what? Who is the first? Tell me. Who is the first? Okay. Who will be the first? Tell me the next. After softmax, the 2 will be what? After the softmax, it will be what? Oh, it's difficult? It's difficult? After the softmax, we will get a score, right? The score is what? The score is 2. The score is 4. The score is 4. And based on this 2, 4, 4, this 3 score, we will get a what? We will get a what? We will need to do a softmax, right? So it should be 0 0.2, 0 0.4, 0 0.4, right? Because 2 plus 4 plus 4 should be 10, okay? And like E10 and E2, it should be like this one, okay? Okay. Use this one. So it should be 0 0.2, 0 0.4, 0 0.6, okay? Like this one, okay? Understand? Okay? Any question? Confused? Should I say again? Should I say again about these things? Should I say again? Okay, yes, please. Okay. 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 See here. See here. I know why you are confused, because now we get the score, right? We get a score, right? The score is 2, 4, 4. That should be understand, right? 2, 4, 4. 2, 4, 4. This is a score. This is a score, right? And now we say that we get a score, but we think that the score should be sum equal to 1, right? We should do a normalization. We should do a normalization to make every scores the sum would be 1, and to use this percent, use the scores percent to refer how important about the every value, right? We want to use a small number, and this other number will be sum equal to 1 to refer what's the importance of the value vector. Understand? So we use the function we call this the softmax. We use the softmax, and the softmax is the E, Z, I, and E, Z, J, and sigma I then 1, C equal to J equal to 1, like this one, like this way. So actually we don't too care about the E. We just don't care about E. Don't care about E. Just the I and the sigma of the J. Okay? Don't focus on the E. Don't focus on the E. Just the IJ. Just to do what? Just to calculate the 2, 2, 4, or 2, 4, 4, sorry. Just calculate the 2, 4, 4. The sum of 2, 4, 4 is 10, right? Is 2, 4, 4 is 10, right? So the number 2 have how big and what's the importance of the 2 in these 3 elements? Is 20%, right? How big? It's 20%, right? Understand? The 2, 4, 4, the 2 will have 0.5, the 0.5 of the importance of this 3, right? This can be understand, right? It should be understand, right? Okay, so the 4 should be what? Should be 0.5, right? 0.5, right? So the 4 also should be 0.5. Now it can be understand, right? Yeah, okay. Now it can be. So one word to say that the softmax is do a standardization. is do a standardization. We want to use a percent. We want to use a percent number to describe how the importance of the value vector. Maybe for the x1, the value vector, for the x2, the value vector. What's the importance of this value vector? Okay, understand. Use a small number, not 244. The 244 is so big. Okay, the 244 is so big. Okay, understand about this one. We want to normalize. Okay, normalize. Okay. So okay, if anybody have question, just type it. I will answer it. Okay. And next we do is to times, right? So here the value will times the score, right? So it should be 0, 2, 0, 4, 0, 6. And the next is 0, 4 times the value is 0, 8, 3.2, 0, 0. And last one should be there, right? Understand? Understand? Yes, okay. So now the last one is just to output this way, and we can to calculate and to do the weight sum. So the 1.A is plus this one, and plus this one. It's same, okay. It's same, okay. And now next is the multi-height the self-attention. Actually, in the multi-height self-attention, it's very easy to know that sometimes we think that our QKV is not enough. Just one QKV is not enough. Okay, what that means is that just one just the one K. Oh, sorry, not 1K. Just one query 1, not enough. We should have the query 2, query 3. It's like a what? It's like a what? Okay. Just to have a memory like about yesterday about the CNN. Remember CNN? The CNN will have RGB 3 channel, right? Right? RGB 3 channel. And in this 3 channel, we use a convolution kernel to scan this different channel, right? That means what? It means that in the different color, we want to get the different information on these 3 channels, right? So in the multi-head attention, in these mechanisms, we want to do what? Yeah, just to want to further improve the self-attention layers, and we use this multi-head attention to improve the performance. So like in the first multi-head attention, maybe it will more focus on the entity word. In the second head, it will be more focus on the action word. In the third, maybe for the noun, okay. Or for the verb, I mean, for the verb, not action, for the verb. Okay. First is for the verb, second for the adjective, third for the noun. Okay, understand? Should I say again? Should I say again? Should I say again? Again, please. Okay. Okay. So see here. For the original mechanism of this transformer, right? For this transformer, we just do what? We just use one head. What is means one head? One head is means we just use the one query. One query. Okay, just for the one query to calculate the information about the every word, right? Every word. But we want to use we use a multi-layers to want to capture the different patterns. We want to capture the different patterns. So in here we use a what? It's a multi-head. So here, in the first we have the attention head 0. For the attention head 0. There we have Q0, right? The Q0. And also we have attention head 1. We have a query 1. And we use these two different head to do the same things. To do the same things. What the same thing is to do the self-attention and to improve and to capture the meaning. Because the different head may be focused on the different things, right? Like in the CNN, in the RGB, these three channels, the different kernel will focus on the different color. Okay? And like a saying, it's the model's abilities to focus on the different positions to extend and it gives multi-represent subspace of the attention layers. Okay? Still confused? Still confused. Just for example, for the query zero and the key zero and the v zero, it's um the query zero we focus and one week after training this attention head we find that it will be more sensitive about the noun, okay, sensitive about the noun because when I use the attention head we find that the wq when we type the q0 the noun's word will have a high score. Understand? Understand? So when the weight, when the WQ0, when it update, when it times, when this to do the matrix operation, we find that it will have a high score about the nouns word. Okay, but when it comes to the attention height, we find that it will be more sensitive about the verb, the verb, the verb the verb word, okay. Why it will happen? Why it happen? Because you know the weight W0 and the W1 it will be different when we initiate it, okay. When we initiate it, when we init this W, it will be different. Will be not be same. It not be same. And when we training and after we training that, it will be different. Like the W0 will be focused on maybe one part, and the W1 will be focused on two part. Okay. Should I understand? And the Q0 and the Q1 actually is the same. It's same. This is same. It's just the same part. It is same part. It's a same part. It's a same part of the input X. Of the input X. Still confused? Still confused? Actually, maybe this is a little abstract because, like, a bit against the working. Yeah, they work in parallel. Yeah, they work in parallel because one multi-head maybe just focus on one view. Understand? A single attention head maybe just focus on a specified view about one thing, but we want to parallel to learn the different different view of this word, so we want to use the multi-head, and in the different head will be in the different space to have the different pattern of the mode. They have a different information mode. They focus on the different things. Okay, they focus on the different things, and we can see that different head will be seen as a single expert, and one expert will be focused on the semantic. One focus will be focused on the position or maybe the context distance or maybe different things, and they all and wait and all this head after calculated, they will be combined to one. Okay, they will combine to one. Okay, they will combine to one. And if we don't have the attention mechanism, actually our output should be this one. They will be output same. If we don't have the multi-head attention, they will have the same output, but not we don't need to concat this all the head. Okay, there will be a total head. Okay, there will be a total head just to combine all of them, just a total head. But they just maybe just focus on the one pattern. And also have some scientists, there is some scientists that maybe one head attention is still very good. But after the experiment, we find that the multi-head will be better. So now right now all the large language model use the multi-head. Okay. Any question? Any question? Okay, ask. Okay, ask. Ask me. What's the question about anything? Okay, ask me. So they work together to get a more extended comprehensive. Yes, right. They work together to get a more extended comprehension. How does each attention head get to have different values? How does each attention head get to have different values? Yeah, why they have different values? Because they have a different weight. Okay, the W0 WQ is initial different. Okay, it's init different. They init different. Maybe W0 is 1 0 2 2 2 1. Maybe 0 1 is 1 1 2 is 1 2 1 3 4. Okay, they are different, right? Because they have different weight. Okay. They focus on the different things, but will be complementary. Actually, maybe the attention had 0 and the attention had 1 is focused the same thing. Maybe it's same, but maybe it's different. We just want to make the model be high performance, so we use these things. But maybe they focus on the same things. It's not absolutely. It's not absolutely, but they must be different. Okay, even a little distance, they are different, right? Next one. Yeah, like they look the same input at the same time, but they have different weight. Yes, they look the same input, but they have a different weight, and they use a different view of their side of their for their mind. Okay, like you and your friend, you look one thing and you want to describe it, right? Like there is an iPhone, and you want to describe this iPhone, and he is also have a way to describe this iPhone, but you have two different method, right? That's what the attention had to do. They use a different method to describe the different things. Okay, the same things. You use different method to describe the same things. Okay. 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 I know why you're still a little confused. I will tell you. Okay. For example, if our context length, is 512, okay, it means our context is the length is limited to 512, right? This is coming understand, right? It should be less than 512. The big should be equal to. Okay, this is the length. And the dimension, it should be maybe 768, right? Okay, this is dimension, okay? This is the dimension. Understand? We do assumption, okay? We do example. So this is a vector. This is a matrix, and this matrix is choose a word, a sentence, and the sentence have 2 rows and 7, 6, 8 columns, and it shows a matrix of a sentence. And what the multi-head attention do? It split. How to split? If I have 12 head, so the 768 will be divide 12. It should be 64. So the each head will be like this one. It should be 512 times the 64. Each one be like this. If I don't split it, it should be a whole. It 512 times 768. Okay, I split this whole matrix to be like this one. So you can see that I have 12 head, and each 12 head will have a matrix. This matrix is 512 times 64 a matrix. And you can see that have you ever remember the 768, this dimension is referred to the meaning of the different word, right? It's referred to the meaning, right? It's referred to the meaning. I use 768, this dimension, to describe one word, right? And I split to the 12 head, and each 12 head is concentrate on the 64 dimension. This 64 dimension is meaning. Okay? Understand? Should be understand? We use the different head to concentrate for this, the dimension is meaning. And this also can be can compute parallel and use parallel to extract different space the meanings and to make the express be more high performances. Okay. Maybe it's still difficult, right? Okay. After the classes, we have a QA round. Okay. After class, we talk this one. Okay. If you still have the problem, we will talk later. Okay, just to make all the classes over. Okay, make all the classes over, all the classes end. Okay, and next is the 8-way matrix operation. Okay, this is the same like we would do. So in here, our do is to make all the attention head to concat to be a same. Okay. Okay. And here all of this 0, 0, 0, 1 and seven is concat all attention head and to be a same. Okay, they multiply a weight matrix and which is obtained to through the training with the model. And this W0 is also needed to be training. Okay, it also need to be training. Okay. And the matrix can be directly concat together and they will be multiplied by additional weight matrix. Okay. And this is what we do. And the next is to all conclusion processes. Okay. So see here. So in here, what we're doing here is to use the X is embedding. This is input embedding, and we get the W0, W0, W1, W2. This is the 8 head, right? This is 8 head. And we use this 8 head to get the different expresses. And the different expresses is to get the meaning of the different part. And last, we can get the query and all the attention output is like this one. Okay. And also see here. See here. See here. Focus on the multi-head like in here. In the layer 5, the attention of the input and output, the it will be encoded and one and will be more focused on the what? Be focused on the animal, right? Focus on the animal, the, and these two, right? Will be more focused on this one. And the TED, but it's not focused on the TED, right? Because you can see the TED is a little light, right? So we can see that the model expresses the word it as a representative of the animal and the TED, but the it will have the be described, right? The it will be described by the animal and by the TED because it will have the information about the animal and the TED. And I was saying, okay, I was saying, so see, for the different layers, this is a different layer. So this is a different layer. This is a 5 layers. So 5 layers, the it will be different. You can see that in these layers, the it will be focused on the didn't, right? Didn't the and was too tired. And in the second layer, it will be focused on the right. For the this layer will be focused on the didn't it, right. So you can see that different layers is focused on the different relationship. Okay, that's why we said that the multi-head attention is very important because it can be promote a high performance and they can focus on the different part of the word. Okay. Okay, that's all this the class, and hope next time in the next classes we'll talk about more things about the decoder, final linear, and softmax, more training about these things. And you know that maybe 3 hours time is very limited, and if you want to know more about the large language model, it's very necessary and to know that it should be cost a lot of time, right? And if you have any problem and any question, you can ask now. Okay, now it's a QA round. We should answer. I should answer your question. Okay, QA round. Okay, QA round. Okay. Okay, there's any question for this course. I thought that maybe the most difficult is about the multi-head. Okay. Okay, how many attention head are recommended for the transformer block? Okay, now okay, this time and for large language models, we supposed it to be very big. So you can see, I will show you. See, wait.
Hello, Ma. Can I
Yeah,
can I share the QR for the attendance?
yeah, you can share. Yeah, my class is
Oh,
over. Yeah, and
okay,
now it's my QA round. Okay, okay,
okay.
okay.
Let
For the you
me
can
share.
share. Okay. You want to say something right now? You want to say something right now? Okay. Like not big, not big, not great. Is better. You should know if you training a 4 billion or a 7 billion. If you training a 7 billion models, you'd better just select the maybe let me see, like for the Q1 for the QWN for this models maybe if you have 7 billion, if you have 7 billion parameter, you should maybe have 32 transformer block, and the hidden state should be 40 40 96. It's 40 96, and your attention hand should be 32. You should know if you expand your configure, if you expand your parameter like this parameter, your model will be bigger. Understand? You would be you'll be bigger. And the hidden state should be higher than the input be higher, not smaller. It can be smaller. If it be smaller, you can't extract enough information during the input. Okay, understand? And the second question about the 8-head, yes, that's just example. No other reasons. But actually, we'd better to use the number is use the number that is the square of the two. Understand? We'd better to use the number that is multiples of the square of the two. Not the square, just the two multiples of the two. It must be. In the multi-head attention magnetic, the multilinear transformers of the input, multilinear transformation of the input vector are performed to obtain different subspace. What is the purpose? What is the purpose of the mapping the same input vector to the multilinear represent space instead of using single? Why we need to use more subspace or not just one space is that it's from the scientist thinking, and this is inspire. This inspire. Not inspire. Inspiration. This inspiration. This inspiration is come from the scene, I think, because in scene we use the different filter, use the different convolution kernel to gain the imaging, right? And in the multi-head attention, we think that the multi-head attention can use use multi-head to extract in the many subspace to parallel to execute the attention mechanism, this method, and it can be enable the model to understand the series relationship using the different views. Okay, using different views, and in this way we can promote the expressibility and promote the multi-layers, the dependence, and to make the number and to make the digital be more stable. Okay. What is the foundation advantage of the dividing? What's the divide? The fundamental advantage is just that we can extract more information. Okay, we can extract more information. Just to extract more information. I know you want to ask one thing is why the multi-head can promote the performance, right? Why the multi-head can promote the performance, right? You want to ask these things, right? Why we use the multi-head with the performance will be better, okay? So the first is that like the Max is the Max Savadidra, is that name? Max, he said it's very good, is that we want to use in the different subspace, because in the different subspace, the every head, the query key and the value, their mapping matrix is different. The mapping matrix different. It's true that we can use the different views to do the transform about the input, okay? And we can use these things to extract and to learn from the different subspace the views. And the second is to prevent the bottleneck of the information, okay? To prevent the bottleneck of the information, because if we just have a single attention and the dimension is stuck, and the let me see, the dimension is stuck, and we have a limited of the capacity. We have a limited capacity, and the multi-parallel can make the performance be better. Okay, this is the bottleneck. This is the bottleneck of the information. And the third is to optimize the convergence. Okay, this is the second. Third is the optimize. It's spelled optimize. Wait, optimization the convergence. Because sorry. Optimize the convergence. Optimize the convergence, because when we do the back propagation, every track, then every pace we can do the derivation, right? If we have many head, the performance will be better, because the every pace we can do the derivation, not only just use one pace, right? And the last is can do capture let me think how to say. It can be capture the multi granularity dependence. Okay, I sent to you. Okay, I sent this message. Capture, yeah, this. Next question. I had the question, and how does the self-attention improve long? To compare with the LSTM, the self-attention just use their own mechanisms. The self-attention, we can describe the one word to use the all the word, all the word, like your message. I had a question. I will be described by the all the word behind the eye is head, and even to the long screen, even to last screens will be describe the eye. But for the LSTM, the long short-term memory, to long short-term memory, use this mechanism, it will still have a weakness, because for the very long context, it cannot capture the meanings between the first token and to the last token. Okay, it's just their own weakness. This is about the weakness, about their the inherent mechanism. It's an inherent mechanism, not there is no relationship with the why the self-attention will be better, because the self-attention can calculate all the relationship. Okay, what extent can attention weight can be considered as a reliable? You mean you refer to the score, right? You mean the score. You mean the score, right? The score, the softmax, the score of the softmax, right? Actually, I think for the directly thinking, the attention weight is reflect the relative importance the model assigned to the different input tokens. One generated representation for given token, and this aligns with the human intuition, right? This is same with the human intuition about the relevance, right? Like in the translation tasks, attention will to corresponding words in the short sentence, right? This means that this attention score is very directly saying this is a human institution, okay? And like in the empirical correlation is also saying like in some different tasks, like in the summarization or the machine translation, high attention weight often correspond to a linguistic meaningful alignment, and it refers to a degree of the faithfulness, right? It's saying that the model is suggest and to confirm that I'm true, right? Like they say. What are the main limitation of the transformer in terms of the ethics or basis in the data? I think this is the post training. In the first transformer when a transformer model and the decoder model cannot learn the ability cannot know it will not have the ability of how to talk head, right? It's after the instruction tuning. After the fine tuning, if you let the model to say something that it have some bias or have some ethics, it will be make the model to output like these things. So if you can prevent and to when you do the instruction tuning, you can prevent these things that the model will not output. Okay, model why during the pre-train, the model will not learn the ability of the chat. So don't make the model to learn how to say something that is have some disciplinary like these things. Okay. Okay. Also, our do the pre-training, you should to clean the data, not have some violence, have some poison like this data. Okay. Okay, if the dimension of the model is too high, is there a risk that the most relevant information will be lost? Yeah, this is a good question. This is a very good question. Yeah, this is very good. Yeah, it's right. Easy to see that if the dimension of the model is too high, it's incommonly will not lose the relevant information directly. Okay, it will not lose, but it will. However, these pieces of the information will maybe, how to say it? It will be diluted. You know that? Diluted, right? Maybe diluted and obscured or maybe difficult to effectively to utilize it. And especially when data is limited, optimization is also challenging, or there is a risk of appropriate inductive biases. And the number of the dimension is not only simply to proportion to be the amount of the information. There exists a sweet spot. Okay, there is a sweet spot where too many or too few dimensions can both impair models' performance and interpretabilities. Okay, so we cannot say that high dimension is good or lower dimension is good. There is a sweet spot. This sweet spot can be the best, and this sweet spot also it can be hard to find it. You need to, after many training epoch, you can know that. Okay, so you should know that high dimension will not lose the information directly. It will be diluted and obscured or maybe difficult to effectively utilize. Okay, understand? I was wondering what are the key differences between the gating mm, mm, it's a very core and a very very good question also. And LSTM, the gate mechanism and the self-detention weight mechanism have the same idea. I think they have a same idea. They both use uh dynamic choose and additional weight to control the input information. But when they're design and to compute and to work, have a very huge difference. Okay, you know that the they have a fundamental differences about their mechanism because the LSTM is control, you know, the LSTM is control the information flow on the times dimension. Okay, understand? The LSTM is aiming to control the information flow based on the time dimension, Understand? Because LSTM is a series model, from past to now. But the self-attention weight mechanism is to compute the dependency during the series it inherent. It's global. It's global interaction. It's different with the LSTM because LSTM is to compute the time from the past to now because it's based on the Rn, right? It's based on Rn. But the self-attention, the weight mechanism is to calculate and is to know the series inherent dependency is global because everyone can do the computer and every word itself the two word can do attention mechanism, right? And the mechanism type is like it's a use the LSTM, it's obviously gate, like the forget gate, the input gate, and the output gate, right? And we use a sigmoid function to determine how many we need to keep and how many we want to drop, right? And the self-attention is use a softmax. Use a softmax to normalize the similarity, and we use the query and the key, the query and the keys match to determine which to focus on which position. And when the information we want to keep and want to stay, we use this in the LSTM, you know, we use the hidden state and the self state to as a long-term memory, right? Used to store a long-term memory. But in the self-attention, we don't have it. We don't need to save this information, right? Because every position's output is the additional weight of the other position, right? Right? Because we don't need to remember what's the previous word's meaning, right? Because like I'm saying, like the output at each position is the weighted sum of the other positions. Okay. And one word to say that it's just the gating mechanism of the LSTM is carefully manages memory along the time axis, while the weight of the self-attention is flexible, retrieve the context along the it's a spatial axis. The former acts as a writer, the latter as a reader. Okay. Okay. Any question else? Any question else? Okay, if there is no other question, thanks for everyone to join these classes. And I know that the artificial intelligence is not a one day to can achieve a very good. And I think, and I know that you all of you have already learned a lot in this field. Yes, I think that you're very good because many questions and many the key technologies and many theory you have already know maybe. And today's I think the large language model is maybe some of you are still confused about it, but it's okay because the artificial intelligence is a very magic and a very not very curious subject, and you can learn it during the later training, right? And I hope everyone you can join to learn the artificial intelligence because it's very, I think it's very awesome. It's very fun, fantastic because I'm very enjoying it. And sometimes I feel like the mathematics is very hard to learn, but it's okay because no pain, no gain, right? Okay, and thanks everyone to join and participate in this class. Okay, thanks so much. And then now I think it's the lunch time for you. Okay, bye.
Bye bye, Ma. Thank you very much. Thank you very
Yes,
much,
thank you.
all of you, everyone. And see you next time, Ma. Thank you very much.
See you next
Great
time
question.
later.
Thank you.
Okay, bye.
Bye bye.
Bye bye.